My name is Renata Branco, and I'll be presenting affordable computation for architecture. So essentially, we're currently witnessing a growth in architectural designs that simultaneously respond to aesthetic, functional, ecological requirements, and many more. And architecture is doing all this by taking advantage of new digital tools and computational-based approaches such as algorithmic design. Algorithmic design, the idea behind it is that instead of us modeling the digital model manually in a digital tool, we instead build an algorithm that builds the model for us. Now, this allows us to create parametric descriptions of our models so that we can generate not one design, but multiple versions of that design, which we can then compare and analyze, of course, to see which one performs the best. We can also then run optimization routines in the solution space to find out which solutions perform the best regarding multiple criteria. And of course, this all sounds amazing, but there is one slight problem to this, which is the fact that these mechanisms are highly time and resource consuming as well. And thus they're often unfeasible within our current project deadlines. So one solution is the acquisition of high performance computing machines. But again, these are expensive, and they're expensive both to acquire and to maintain. And unfortunately, only a small fraction of architectural studios can afford this sort of high performance computing. So the next step is remote high performance computing, right? Where we have even more resources available to us, as many as you'd like. Sky's the limit in this case. And this allows us to save time in these computations, and doing so also at a lesser cost. And what we envision for the future is that just as we already benefit from common contracted services like water, electricity, gas, or cable even, which are already being provided to our homes via their own distribution networks, we can just add a new block to this list, which is remote computation. There's just two slight problems to this: batch processing and task partitioning. And I'll explain what I mean by these concepts. So in high performance computing, we are essentially submitting tasks to a remote computing service and receiving the results only after completion in the end. So there is little interactivity in between in this process, which means that we must carefully plan and test our tasks in a small scale before we send it in a large scale, just to make sure that no errors occur in the process. The other challenge is precisely the scale. So although architects are typically more used to visual programming languages, as we've been seeing here before, and the case is that for large scale endeavors, textual programming is actually the one that will do the job. The second issue is the fact that, well, high performance computing means that we have several machines at our disposal, which implies that we have to divide our tasks, right, and allocate them to the existing hardware, meaning that we essentially are parallelizing, right? In order to do things faster, we have to parallelize those parts of the task that we want to do at the same time. And this immediately takes us to the types of tasks that can be easily separated, right? Independent tasks, such as rendering each pixel in an image, for instance. And these are the tasks that we call embarrassingly parallelizable. And there are many more. And you can also think of rendering each frame in an animation or a film, for instance. And some tools are actually already prepared to handle these parallelization cases automatically. But of course, this is not the case for all processes. For instance, you can picture an optimization that depends on previous results to conduct a search on the solution space. And obviously, that is a less parallelizable case. Another example is the analysis process, an analysis process that requires the use of a single thread tool. Of course, again, we have a solution for this. We very rarely want to make just one analysis. Usually we want to make multiple, and the solution in this case is obviously just making them all at the same time. And the same goes for optimization processes. So we decided to put this into practice with a case study, a truss structure using catenary curves placed on a slab with a randomized outline. We just wanted the truss to have, not to have an axis of symmetry, so it could be a more interesting resistance case. It could be interconnected with different truss schemes and using different materials. And we modeled it and analyzed it using the Kepler tool. And Kepler communicates with several other CAD beams, analysis, and rendering tools. And of these, we selected those that already benefit from parallelization, Povray and Frame 3D, from batch processing, actually. And the whole thing was developed in Julia, which is Kepler's chosen programming language, and it also supports multi-threading and distributed computing already. So we focused on 3 design tasks: analysis, rendering, and optimization. And regarding the software, the hardware that we had, the evaluation was conducted on a supercomputer containing 4 computing nodes, each providing 96 threads and accessing 512 gigabytes of RAM, which in total essentially allowed us to use 384 simultaneous execution threads using 2 terabytes of memory. And this is pretty impressive, right? This represents a significant amount of computational power when you compare it to current commodity hardware. So your standard laptop will have 8 execution threads and 16 gigabytes of RAM only. The analysis task tested a vertical load of increasing magnitude on our truss, and for each load case, the structure was analyzed on Frame 3D and then rendered in Povray just to see how the shape behaved under load. And each structural analysis, here's the parallelization scheme. So unfortunately, each structural analysis was entirely sequential, which meant that we cannot benefit from multiple threads on a single evaluation. But luckily enough, the most time-consuming task in this process was actually not the analysis itself, but the rendering of the results. And as we saw before, rendering is already a highly parallelized task. So Povray took advantage of the 96 threads every time for every case. We also wanted to measure the scalability of Povray. So we experimented rendering these image sequences in 2 sizes with increasing numbers of threads for each task. And you can see here the graphs showing the results of the time spent for each case and for the different numbers of threads. And the time per image using 96 threads was 30 and 110 seconds for the small and large resolution image, respectively. And just to have a measure of comparison, in a typical PC, we would, again, be likely limited to the 8 threads, as I said before, which still using a supercomputer, which is the numbers you're seeing here, took 214 and 857 seconds. All right, this already represents an 8 times slowdown, and we are only comparing the number of threads. On a desktop, depending on the hardware, the slowdown could be even bigger. So joining the 2 graphs so that we can focus on the speedups. For the smaller rendering, it actually only paid off to use up to 80 threads, but we obtained a speedup of 40 times. And in the large image, we were able to obtain a speedup of 40 times faster, and the trend line clearly evidences the potential for more if we kept increasing the number of threads. Finally, the optimization experiment evaluated the best location for the truss central node according, obviously, to the truss's structural performance. We began by applying a vertical force and then actually added an horizontal force just to increase the variability of the objective function landscape you're seeing there. And we used 2 different optimization strategies. They were both population-based. You never know which optimization algorithm is going to perform the best in your case study, so you should always test multiple, and that's what we did. And they both called the structural analysis tool Frame 3D to evaluate the objective functions, and these are essentially the parallelization schemes that resulted from this process. So as before, we repeated the test with different numbers of processes to evaluate the scalability, and the results show that the optimization clearly benefited from the parallelization, but only up to 8 processes at the same time. So in either optimization strategy, they're both the same. So what we conclude here is that unlike the previous experiments, the gains of the supercomputer did not surpass those of a normal laptop in this case. We do conclude, however, that high-performance computing, it proved useful for architecture, and then in this small case study of ours in particularly, namely in these 3 design tasks. Of course, the analysis task was pretty much overpowered by the rendering task, but the rendering task did have very good speedups, and even better ones can be foreseen. Now, the optimization task was not as successful, so for the algorithms used, we concluded there was no gains in using more than 8 threads. Knowing all the while that evaluating them all will take no longer than running the slowest of them. And this is pretty essential in architectural optimization because, as I said before, you have to test multiple algorithms. The no free lunch theorem tells us that no algorithm consistently outperforms all others in all cases, so we must find the one that fits our case the best. Regarding the two challenges that I presented before, they were surpassed here with success, although I must say after several trial and error loops and with a high dose of manual labor, leaving us with a list of future use prospects. So the first of which is the fact that high performance computing provides very little or to no compatibility with the tools that architects typically use. So we need to find workarounds for this. Also, not all software nor design tasks can benefit from high performance computing directly, and a parallelization strategy must be devised for each case. And even in the processes that do directly benefit from parallelization, the performance improvements are variable. So their limits should be tested and known before we launch processes in a large scale, just to make sure that we're not simply wasting resources. And finally, it really only pays off to parallelize if the time it takes to start the process is significantly smaller than the time we need to complete the process. Otherwise, instead of speeding the computation, we might just end up slowing it down. And finally, circling back to the goal of this paper, which was affordable computation, despite the huge computational power of the supercomputer that we were using, its operational costs are rated at 1 cent per core hour, which means that even using all the available resources, which we did not, we pay less than €4 an hour, which is an enormous cost reduction when compared to the acquisition and running costs of a personal workstation, or in any case, the workstation that you'd require to handle these sort of demanding computations we're talking about in reasonable time. So I hope I convince you to at least give high performance computing a try. And if you have any questions, these are our contacts.